Zero Knowledge Rollup. We started building on the OP stack. We're not on the superchain, but we do love what they do. And we want to talk to you about some of the struggles we had in making their code our code. And the big one that we had over the last couple of months was this thing called a zkTrie. And if you don't know what that is, hopefully in the next couple of minutes you're going to find out. So let's get into it. A little bit of background for you. I'm going to target this in a really weird place. I'm going to assume you know what a rollup is, so I'm not going to go through explaining that. If you don't know, there's a couple slides where it might become very clear what it is, but it's easier if you know. So apologies if you don't. If you have any questions, come find me afterwards. Happy to explain. Also L2s, types of rollups, other things. And we'll also assume a little tiny bit of OP knowledge and Zircuit. And basically, I just want you to know that the OP stack generally builds optimistic rollups. This may be changing now with OP succinct and other things. And Zircuit is a zero knowledge rollup. So it's a key differentiating factor. Zircuit's also got other unique features, which we would love to talk about, but they're not the focus of this talk. So I'm going to skip that. But nonetheless, let's get into it. The title is bringing a zkTrie into the OP stack. Why do we want to do this? Well, the first one is just, can we? Like, I'm a technical person. I want to see what the challenges of this are. Maybe I get some benefits out of it. And it turns out sometimes you might. Those times you might is when you're trying to build a zero-knowledge proof, or zero-knowledge rollup. Because you have to always use this zkTrie, or rather the MPT in Geth, to sort of show that you've updated state correctly. And the one that currently exists by default on the OP stack and Geth and other places is a Merkle-Patricia-Tie, which I'll talk about in a minute. And that is apparently not very good for zero-knowledge proofs. It does operations that zero-knowledge proofs take a very long time to do. And it does this because it's built on this notion of KESAC256, which is a famously good but zk slow hash function. So if we could change that to something that's a little bit more favorable, like Poseidon, you've probably heard this all over the place, that's not so bad for zk proofs. So let's see if we can do it. Spoiler alert, we did. But before we get there, I want to talk to you about what we're actually talking about. Because I just realized that last slide, I dumped a bunch of jargon on you. So what am I talking about with the zkTrie? What do I care about? Well, rollups have to post summaries of their state to other places, right? So they have to post to the layer 1, to Ethereum itself, in order to inherit some of that security. Basically, they post an updated root, and everyone agrees through some smart contract rules that final root is the real last thing you've seen on the L2. And therefore, unless you can change that on the L1, there's some level of security. So that's really helpful and useful and very, very effective. And typically it's done through something like a Merkle-Patricia-Tie, or this plus some additional data, or this with various other things in it. And a Merkle-Patricia-Tie just sort of looks like this. It's a tree-like data structure. It's a trie, technically, not a tree, so there's some sorting in how leaves are placed, but it is very much like a tree. And every node is sort of the hash of its children's node's data. And if you're a branch or if you're a leaf node, you just hash the data that's in it. And essentially, this means that if you change any piece of data, and all of the data you have is eventually hashed into a single root, the whole root changes. So any small change anywhere in the blockchain or in this data set will result in the root changing. And if you just change that root then and just update that root, I can be very effective at posting a very short summary of my data. And the root is just the thing at the top that is dependent on all the other hashes, right? This means a change to any of the data in the leaf nodes changes the root. So if you update a balance of an account, the root also changes. That's critical. So you can't get away with cheating, because every time you make a change, the root's going to change and you have to post a new state root. So because of how this is built, there's a lot of hashes going on. And so when I say KESAC256 might be too slow for zero-knowledge proofs, I'm not just concerned about doing it once or twice or some small amount. I have to do this every time I update any state in my rollup. And so I'm using this a lot. So if I can get some optimizations, I'm really happy to do this. So where are they used? And what happens with them? Why do I really care? I've told you about this data structure. Well, these are summaries for rollups. So let's think about how a rollup works for just a second. You have this notion of an L1 in gray. You have a sequencer that builds blocks. Maybe people call it a different name. Maybe there's a block builder component that's slightly separate. Doesn't matter. You get some transactions, either from other people interacting with the network directly, or bridging on to the network from L1, deposit transactions. You build some layer 2 blocks, and then you propose that to say, this is my new state root. and you post it on chain, it's sort of locked in, subject to these rules where the verifier might interact. The verifier in an optimistic rollup is the fraud-proof system or fault-proof system where someone might challenge you and say, actually, you did all of that wrong. I saw your MPT. I saw your list of transactions. You cheated. Let's fight. And you do something. In a zero-knowledge proof, it's less explicitly an actor and more just a smart contract that verifies a mathematical proof that accompanies this. And that's where we want to go. But I'm talking about the OP stack, so I've got to include both. If we look slightly more specifically at the OP stack, these components have real names and real pieces of code associated with them. They're not abstract. There are various things that need to change if you touch a state trie, and we're going to talk about this. So the node, the sequencer, is sort of a coupling of an OP node program, which sort of drives the consensus for the OP stack, and an execution engine, OP-geth, which is a fork of geth that they've modified in some ways to produce layer 2 blocks on Optimism or any other OP stack chain. And then they have an OP proposer, which occasionally takes all that stuff, posts it to a smart contract, and then the op program can be used to challenge these things. So you start seeing all these components, and actually there's probably a dozen others that you may or may not want to touch if you're screwing around with an OP stack code base, but there's a whole bunch of stuff you can change. And so let's see, where do we have the zk or trie or the MPT trie? Oh, it turns out everywhere. Right? All of these critical components are going to be touched by this MPT. So now if you want to say, change your state root summaries to be a zkTrie, you can't just go to one piece of code and say import, to Poseidon instead of Kesek 256. That would be great if someone could refactor that code base to make that work. That would be huge. I don't think it's feasible. I think we got to go component by component. And at Zircuit, that's actually what we sort of had to do. We wanted to go through and take out this MPT and put in a zkTrie. And so we started looking at all these things. And I'll tell you, we got a little bit lazy. And I'll tell you a little bit how in a bit. But let's go through why we needed to do this and why we couldn't skip any of these steps, or at least we had to skip them in a clever way. First, the OP node. It's the consensus layer. It's sort of responsible for actually instructing the execution engine to build the blocks. It is going to get deposit transactions from L1. It's going to get other things. It's going to rederive the state when needed. So if your node goes down, you can run it up, and it can read from L1 and rederive all the chain. So unsurprisingly, if it's trying to rederive or build blocks for the L2, it's got to touch the state trie. It's got to figure out what's going on. One really important place it does this is a function called prove withdrawal parameters for event. It's a complicated name, whatever. The idea is that this gives you that withdrawal proof. So at the end of the day on an OP stack system, you have to prove as a user that you submitted a transaction on the L2 that was eventually written to L1 as part of the state. And you need to call this function somehow indirectly. Probably you don't call it, on your console, but somehow this is called. And that means it's very critical, and everyone touches this. So you can't skip this, because then you screw with people's withdrawals, and if people can't take money off of your chain, they're going to be really upset with you. So you got to touch it. There's a couple other places in this derivation stack that also touches the trie and the state summary. The next one is to actually build this summary. Sort of the obvious candidate shows up, geth, or the thing that looks like geth, OP-geth. I might call it L2-geth, because that's what we call ours. It's sort of the obvious one in the sense that it is responsible for changing state balances and accounts based on transactions. When you make these changes, therefore, you have to update the summary of the balances. And this is where probably the largest number of touches to the code base needs to occur. You need to go into a bunch of places into geth to figure out exactly when this tree is read or written to, and update it and change it to, say, the Poseidon-based zkTrie that you care about. And it does a whole bunch of stuff. I'll go through some of it. For the people who don't know, it's definitely going to do at least the following, where it'll store a summary of the nonce, a balance, and a storage root, or the code for contracts. So basically, it really takes the whole summary here. And then it'll update the trie in such a way that it remains a trie, not just a tree. It'll order things in an appropriate way. And then finally, it does all this hashing, and you're done. But if you want to execute that correctly and quickly, you do need that zkTrie. Once you get all of that changed, it's the biggest piece of code to change by far, you have to submit the new state root on chain, and then you have to tell people that actually it's going to do something different. And now if you go back to derivation, maybe you need to use a different function to change the withdrawals, or you have to have made that change. And essentially, it touches the output. No surprise. This is great. So these are the three sort of things that we really cared about at Zircuit because we wanted to switch to a ZK rollup, but there's also verification. So the challengers then also need to be aware of this change. So you can't run a zkTrie OP stack with a fault program in MPT out of the box. I would imagine it'll be very difficult to do it all, but you have to make this change. And so the fault program also needs to be updated. And basically what this means is you've touched very critically almost the entire stack. This is a non-trivial challenge. I encourage you to try and play around. I think it's a fun thing to do. You really understand how transactions flow work if you can trace where this trie is updated in red and touched throughout this code base. Especially if you're here as a hacker, it's something that's very interesting. And in a couple slides, I'll tell you why that might still be interesting, even though this is very hard and will take you probably longer than a week. But essentially, yeah, you still need to touch the verification. OK, so let's take a step back. Why were we doing this? We wanted to get faster proof generation on blocks that were now built using a zkTrie, not an MPT. And in short, there's a lot of work. This took us a ton of effort to do. There's, as far as I know, no good open source fork of the OP stack that uses a zkTrie. We're going to open source our code base soon, so maybe ours will be one that's really helpful. Other people have done similar things. So Scroll, for example, has put a zkTrie into Geth, but not necessarily the same version of Geth. And because they're Scroll, they wouldn't have touched like OP Program or OP Node. They'll have their own versions of these systems, which is totally fine. But it's a lot of work. So it was a challenge. And we wanted to do this for ZK rollups. And because it was so much work, we thought we could do something a little bit different. And we just released a testnet earlier this week where actually we are doing something different. We are going to touch this code base in only a couple of places. We're actually not going to touch too much of the OP node or the OP, the proposer will change. But we're actually going to have our Geth computing both tries so that we can actually have the OP proposer still write an MPT state root that's normal and fine, and then we can also generate a proof for a zkTrie, and we can make sure that those are mapped sort of one-to-one, or one never falls behind the other in some nice, safe manner, and people can have the UX of working with an MPT from the OP stack, but also we can get the performance and the proofs from a zkTrie. This is not a long-term strategy. Right now, we're doing this in part because we want to see if we could, in part because we needed to increase performance. But in the future, and I'm going to talk about this on the next slide, we want to know what we're going to do with our chain, and probably a bunch of other people on OP Stack chains also want to do this. In particular, this may not be super relevant if we change back to a ZK VM. If we go find something like RISC-0-based general purpose ZK VM, it doesn't really care too much about the trie that you use to record your state. There might be performance hits, but it might not be as important as it is right now, where Halo 2 really struggles to do Kasak. And maybe it'll be worse, I'm not sure. But we want to have this flexibility, and in the next version of our release, whatever that looks like, we'll pick one of the tries to be final and say we're good, right? But so this flexible approach that we're taking for now is really nice and helpful. And why you might also care is that this might not be the last time you have to touch this code base, like you as a community or you as a developer. In the future, Ethereum wants to put Verkle trees inside Geth, and maybe that means all of the OP stack needs to change for that again. So getting good at this or modularizing this now would be really valuable. Now, I'm not saying that's an easy task. I'm not even saying it's a feasible task. But a man can dream, and I think it's worth trying. And at the very least, you can play around with it now so that when you want to make these changes later, it's maybe not so scary. But either way, I think it's an interesting technical challenge. I'm basically out of time. I got only one last thing to say, which is Vitalik tweeted this the other day, and it sort of gives exactly a good reason as to why this might be prominent, because he says they might want to switch just that Kasak to Poseidon for native L1 clients. And that means if Optimism or other rollups want to be exactly one-to-one with the Ethereum node on the L1, you would have to do this anyways. So all of the stuff I talked about, we have to get good at practicing and doing right. And we hope we did it right. We got audits. We checked all of that stuff. But other teams should also take on this challenge, and maybe we can make it easier or better. And this is not just like an exercise in can we do it because we have engineering manpower lying around. It's something that might be very necessary in the future. So I think it's a little bit more wider reaching than my title suggests, but still interesting. Anyways, I'm out of time. I have no more slides. if you have any questions or concerns, come talk to me. We got a booth down there. Just go that way. We have plushies, and I'm happy to answer any questions and discuss Zircuit or our modifications to the OP stack there or online through one of these methods. So thank you.